Hi everyone. So I'll be talking about Bandit, a field that I really don't know much about. But what brought me here to this field is really just a question of changes in distribution. So I've been working a lot in domain adaptation and such, and just trying to see whether some of the ideas in domain adaptation can be brought into Bandit as distributions are changing over time. This is based on joint work with my student Joe Suk, who's really been taking the lead on this project. First, although I'll be mostly talking about Bandit, first let me just set up a long-term motivation. More generally, we are interested in sequential decisions under noisy partial feedback. So sequential decisions under partial feedback. And so there are various problems there. There's contextual bandit, there's RL, there is all sort of tracking problems. And generally, it is clear in a lot of these problems. And so there are many applications. I have these little cartoons there for the various applications. The one thing that is clear under all these problems is that if the environment remains consistent, then we may eventually sequentially learn a good policy and start making good decisions. However, in the real world, the environment changes frequently, right? And so we have to try and understand how to best adjust to such environmental changes. So there's tons of work on these type of problems. And the flavor of much of this work is try and detect changes quickly. So in the first talk, we talked about change point detection. So that's the flavor. Try and detect changes quickly enough, and then restart the learning process. Okay. So, and the usual guarantees are trying to compete with an oracle that knows the time of changes and restarts every time. All right. So the basic question we are asking here is this actually the right thing to compete with? Because the moment there is a change and you restart, you've lost all information acquired in the past, right? And so it's a question about the severity of changes. Are all changes severe? I hope that's clear. And how severe are these changes? And do we need to restart? And in which cases do we need to restart? So first, we want to try and understand a notion of severity of changes or define such notions, quantify the severity of changes in particular problems, and then ask the question of adaptation. Adaptation here, what I mean by adaptation is without knowing a priori the severity of the change, can I adapt to it? Can I get a rate that is in terms of that severity? And can I also restart only when I need to restart? I hope the motivation is clear. So we'll focus on contextual bandit, contextual bandits in general. So I'll define first contextual bandit. It's a far shot from the eventual goal, but it's a good place to start. Okay. So contextual bandit, at time t, so we observe a context xt, here a patient that comes in, a patient profile. We observe a context xt, and then we pick an action A out of a finite set of actions. It's a treatment, but it's a treatment geared at that particular profile of the patient. Okay, and then we observe a reward, yt of A given xt. So a reward being the outcome, like did we do well? Is the patient recovering? So in this particular problem, the context distribution, so the arrival of patient, the profile of patient, the population itself may be changing. And also the reward distribution may be changing. So our treatment may no longer be working. Okay? So all these things may be changing. And the question then becomes, when are these changes severe and can we adapt to them? And how can we measure the severity of such changes in contextual bandits? We only have partial answers so far, and because the way we want to proceed here, the way we proceeded over the last 2 years, is to break up the problem, to look at different types of changes separately. So changes in context only, changes in rewards only, and try to understand this basic question, when are these changes severe, and then eventually try to combine all of that, right? So this will be essentially the outline of the talk. First, I will consider changes in reward, YT, distribution. And in fact, I'll simplify the whole problem. It won't be contextual anymore. There will be a single context if you want. So it's just regular Bandit. There is just a set of actions, and I have to pick the best action. The distribution of actions is changing. Then changes in context distribution. Again, we simplify the problem. Only the context distributions are changing. The rewards, conditional reward distributions are not changing. And then we try to bring it all together, and this is ongoing work. Okay. All right. So changes in reward, YT distribution. So this is non-stationary Bandit. At time t, we have a finite set of actions. We select an action, A, out of the set of actions. We observe a reward YT, and the mean of the reward is going to be denoted mu t. The mean of the reward will be denoted mu t of A. Okay. Now, I'm calling it mu t because here it's non-stationary. We are assuming that the mean is changing over time. All right. So we are interested here in this notion, the dynamic regret. And the dynamic regret, here AT just means the action we picked at time t. And we're comparing it to the best mean reward at time t. Okay? And so this is a very tough quantity to try and compete against. The whole difference, I call it delta t of AT. All right. So this problem has been studied quite a bit, and what was known is what I'll go over. And we have to try and parameterize the problem somehow. And there are different choices of parametrization of the problem, and I'll go through them. The most basic choice of parametrization of the problem is just count the number of changes in the mean rewards. Okay? And the main question underlying all these parametrizations, however, is that of adaptivity. Can we adapt to this particular parameter? So without knowing the parameter a priori, can we get the best possible rate in terms of those parameters? So in the middle column here, I have the best oracle rate, where the oracle knows the parameter itself.
I just want to make sure I understand. When you say L changes, you mean L changes over the horizon T?
Over the horizon T.
Or L specific? Yeah.
L specific changes in mu t, in just the mean reward. Gotcha. Okay. So that's the most basic. Why? Because again, that's the point I was trying to make, is that we are interested in adaptivity. Can we adapt? It so turns out that we can relax the notion of change, but we may not be able to adapt. Okay, and that will come quickly here. So L changes, the best oracle rates are known, square root LT. Okay. However, it took about 10 years to get adaptive rates, to get an algorithm that actually adapts and can get the square root LT without knowing L a priori. All right. However, we do realize that all changes are not here. It's clear that all changes in mean rewards are probably not severe, because if the best arm has not changed, we probably should not care. Okay, so S here is the number of changes in best arm. However, here we know that the oracle rate should be something like square root ST. Here I had a little problem here as to who to credit for this rate. You'll see that I credit Peter Auer in 2002, and yet this rate subsume the rate above where I credit Gary V and Molines. But it's because the assumptions are a bit different in all these papers, and it's hard to give attribution correctly. So in any case, it was known that in terms of best arm switches, the best rate should be about square root ST. But it's remain open whether there is an algorithm that can attain the square root ST rate. So then there is also a whole other line of work, which is that of total variation. I'll define what they mean here by total variation in a second. But the main idea is that rather than counting the number of changes or the number of best arm switches, maybe we should look at the aggregate change. By how much have the means changed? Okay. And so the best rate is this somewhat ugly quantity here. and it is achievable adaptively. But I'll compare these various formulations a bit later. Okay. So what we show is that in fact a much weaker notion of change also admits adaptivity, much weaker than number of base arm switches and such, and in fact close that open problem that base arm switches can be adapted to. So one of the contributions is a new notion of significant shift, what we call a significant shift, and which would only count the most severe changes, which I'll describe in a minute, the most severe changes. And the most severe changes here, some base arm switches can be ignored, some large total variation can be ignored, okay? And the rate of this form, the adaptive rate, for the number of significant phases unknown, takes this form where we sum over the significant phases and square root of the length of the significant phases. Okay? This is always faster than square root st, which is always faster than square root lt, and which is in fact always faster than the best rate achievable in terms of total variation. So somehow the notion of significant changes or significant shift subsumes these other notions. All right, so to give intuition as to, before I define a significant shift, I'll just give some intuition as to what changes we can ignore. Okay, so here are base arm switches, and what I'm doing here is I'm letting, imagine that, so we have just two arms, A and A prime. Imagine that arm A prime becomes best, but its mean is only so much better than the mean of the other arm. Intuitively, we should be able to ignore that. I hope that's clear. It's gotten better, but just by a small amount. The other way we can ignore that is arm A prime has gotten better by a large amount, but for a short time. I hope that's clear. And so a lot of base arm switches can in fact be ignored. If we were counting all the base arm switches, then we may, in this type of case, get an upper bound of order t, which means no learning. And yet, what we show is that in these cases, the upper bound is still square root t. Okay? And in fact, going back to what I said earlier, in fact, we don't need to restart in these cases. Okay? Total variation, the way total variation is defined is this way. It's sort of a worst case notion of total variation, where we're looking at every time t, every arm, and looking at the worst case change from time t to time t plus 1 of every arm. Okay? And here is another simple cartoon where I show that, okay, we can make this quantity very large, and yet this change need not be detected. We don't need to restart. I hope that's clear. The quantity is very large, but the base arm has never changed. We don't need to care. Okay? And so this is a case, again, where I can bring the best bound in terms of total variation to linear in t, and yet we can still get a square root t regret. Okay? So here is a change that we cannot ignore. So again, we only have two arms. What happens here in this change is that on aggregate, arm A prime has become really bad at some point in time. And then on aggregate, eventually arm A, which remains safe till now, also has become bad. So there is no safe arm left that we cannot ignore. And that leads immediately to our notion of significant shift. Our notion of significant shift just says that there is no safe arm left to play. Okay? And here is a simple way to formalize it. For any arm A, there exists an interval where the regret of the arm, dynamic regret of the arm over that interval is greater than square root of the length of the interval. Okay? So there is an interval where it's doing really bad. Every arm. All right? So that's the notion. It immediately implies base arm switches, because if I take the best arm, at some point, if the best arm never changes, then delta T of A is 0. So this could not have happened. So if this happens, the best arm has switched. I hope that's clear. And also, it's not just that the best arm has switched, but it has switched by a significant amount, so that it also implies large total variation. Okay. So for sanity check, an oracle that knows this, so now having these defined significant changes, we have significant phases, which are the times in between. And an oracle that knows the significant phases can achieve this rate, can achieve the rate that I showed earlier. So our whole point is to try and compete with this rate. The reason an oracle can achieve this rate is that by the definition of significant change, during a significant phase, there was a safe arm till almost the end of the phase. So the oracle can just keep playing that arm. I hope that's clear. So that last safe arm is the arm the oracle just plays, and then it incurs regret square root of the length of the phase. So the whole point now is to try and track just that last safe arm, A sharp. All right. So now we want to track that last safe arm. And one of the key insights I'll give first, so I'll talk a bit about the procedure. One of the key insights I'll give first is that rather than in a lot of previous works, what people try to detect, the type of change point detection, revolved around detecting changes in the mean rewards. Okay? So here, all of a sudden, we're not caring about changes in mean rewards. In fact, hopefully you see that the definition itself allows that there is no stationary phase. I hope that's clear. We can have the distributions changing all the time as long as it's not a significant change. Okay? So the notion of a mean reward changing is not well defined. So here what we'll try to track instead is this aggregate regret. Okay? The aggregate regret itself has this mu t star in there. The dynamic regret has this mu t star in there. That's the reward of the best arm. We don't know it, so we cannot track it. What's nice is that, again, this A sharp, which is the best arm in a phase, itself has small dynamic regret. Since itself has small dynamic regret, and I said it earlier, all we need to do is actually try to do as well as A sharp. Okay, so what we'll track in the algorithm is just the relative regret between A sharp and any arm A. Here, because we don't know A sharp, I'm writing A prime A for any pairs of arms. Okay, so that's how we'll track. All right, we need to be able to estimate this, so I'll take a quick aside to talk about how do we estimate this. So to estimate this quantity, we just use this weighted, we'll use a weighted mean, okay, where we reweigh the mean of every arm, the estimate of the mean of every arm by the probability of playing that arm. And so this right away tells us one thing, is that we need an algorithm that is stochastic in nature. So we have to randomize, it has to be a randomized algorithm, we have to randomize the place in order to be able to use this estimator. Okay. Now the estimator itself is concentrated and concentrates very well. You can quickly see that it's a martingale and it concentrates very well. The only thing here is that you have to use a Bernstein-type martingale inequality to get the right concentration for this. So now, that said, let's view delta hat t of A prime A as the same. We will conflate the two. Okay, we just can conflate the two now. So here is the procedure. We evict arms whenever on any interval we incur some regret with respect to some other arm. I hope that's clear. Now, because the world is changing, the evicted arms can have become good all of a sudden. So we need to replay. We need to replay the evicted arms at a particular schedule, at a particular interval. And then once we replay evicted arms, some evicted arms may force us to evict the arms that were retained so far. Once all the arms have been evicted, that's the end of an episode. Now we start a new episode. Okay? We have detected that there is some significant change that has happened, and we restart. So now the algorithm plays episode by episode. And the two main quantities now becomes this A sharp, the last arm that was safe within a significant phase, and this A hat sharp, the last arm that was evicted in an episode. And then the guarantee will just come from trying to understand the relation between these two. Okay? All right, so the main thing here is designing random replace. Let me see how much time I have. Yeah. Designing random replace is the main thing here. And so how do we design random replace? There are two considerations that are sort of opposite each other. The first consideration is that of critical segment. And I'll define in a second what I mean by a critical segment. Here, I think a picture is better. A critical segment here, I fix any arm A, and then I'm going to say, at what point should I evict A with respect to A sharp? And there is that segment of time where A all of a sudden has really bad regret with respect to A sharp, and that will be considered a critical segment. And then the whole point will be to design the random replace so that I can detect these critical segments. I hope that that's sort of clear. I'll skip through this quickly. But then there is a notion of ideal replay. An ideal replay is one that is scheduled right at the beginning of a critical segment and lasts as long as the critical segment and can detect that something has changed and throw out arm A. Here, I guess if I go back to the picture, you can see that if I start a replay at the beginning of a critical segment and lasts long enough, A sharp is good in this whole segment, and A is really bad with respect to A sharp and can be detected that it's bad with respect to A sharp over that segment. So the whole point is this critical segment and this ideal replace and how much, how do we schedule this ideal replace? And we want our scheduling probabilities to be large enough so that we have a chance of landing inside this critical segment. And that's the whole point there. Okay? And we schedule replace of different length in order to catch segments of different length. All right. This immediately would imply to us that this A hat sharp is good with respect to A sharp, since it wasn't rejected. Every ideal replay would have rejected it. I hope that's clear. All right. Then the other thing we have to consider is the cost of replaying. If no change has happened, then we don't want the replays to force us to incur too much regret. So we don't want to schedule too much replays either. So those are the two conflicting things. Okay.
Would you mind reiterating the notation? So A sharp.
A sharp was, yeah, so here, A sharp is the last good arm in a critical phase.
A lower sharp.
A hat sharp. Yeah. Oh, it's the hat, really. Yeah. A hat sharp. Actually, I should have put the sharp down. Yeah. A hat sharp is just the last arm in the episode. Okay. And so literally all we've said so far is that if we schedule properly, then the regret between A sharp and A hat sharp is not that large. And all we have left is to show that the regret of the algorithm itself with respect to A hat sharp is not that large. I hope that's clear. Right. And that now comes to not scheduling too many replays. If you schedule too many replays, then whenever there is no change, those replays are replaying bad arms, and the regret could go large. So you don't want to schedule too many replays either. And so the sweet spot is having the scheduling probability about square root 1 over Tm, which works well. And it's actually quick to see that it works well because every replay contributes a relative regret of about square root m. And so multiply that by this, and you keep approximately a square root t regret. Okay. All right. The scheduling turns out to be similar to these previous papers where they were trying to do actual change point detection of mean rewards. Okay. All right. I hope so far that's clear. You can stop me, please. Yeah.
So, from what I understand, you have a set of A-sharp arms, like there's a set of like good arms that could be A-sharp, and you're maintaining this sort of active set of candidates to be A-sharp.
Exactly.
And is that set always shrinking until the end of the interval, or is it constantly changing?
It's shrinking. Yeah.
Okay.
Yeah.
And so it only decreases a small, and then you start a new episode.
When a replay comes in, we replay every arm. So during the replays, every arm is replayed now.
I see. Okay, so you're always comparing to the other arms.
Exactly.
You're constantly always playing those, but the candidate set of being A-sharp is constantly shrinking. Until
so we have a parent algorithm that is shrinking the candidate set, and then you have replays that are scheduled in between. And those replays that are scheduled in between are just trying to detect, are we still confident in these candidates?
Got it, thanks.
Okay. All right. So as a result, so this is essentially the analysis itself just follows this intuition that I laid out. And as a result, we get this, that the regret is very similar to the regret of the oracle, up to log terms. The regret of the oracle up to log terms. It's always faster than square root ST, and always faster than the regret you get in terms of total variation. Those just come as corollaries to these results here. After we posted the paper, there was an archive paper posted a month later, which independently gets the square root ST rate. They don't have the notion of significant phase. They were just trying to see if they could get adaptively the best rate in terms of number of best arm switches. Okay. But again, what we're arguing here is that best arm switches itself is still too pessimistic. All right. So an open question here is whether our notion may be further weakened. Because I gave this talk a few months ago, and Philippe Rigolet was asking me, okay, why should I care? You just came up with a notion that is much tighter. What if tomorrow somebody comes up with a notion that is much tighter? So that's really the open problem, is this the limit of what we can adapt to, right? And how do we even try to understand these limits? We have a bit of results towards that, but I'll try to talk about that at the end if there is time. Okay. All right. So changes in context. So we looked at changes in rewards separately. Now we want to look at changes in context. And in fact, we'll take a covariance shift type approach. I'll explain covariance shift in a second. But all I mean by covariance shift is that the conditional rewards given a context remain unchanged. And we just want to understand the effect of changes in the distribution of context. All right, so here's the setup. At time t, I observe a context xt. I select an arm, and I observe a reward for that context. Covariance shift, I just explained it. The distribution of xt is changing, but the conditional means are not changing. Okay. And now, here we are interested in a stronger form of regret, which I call the interval regret. Okay. Earlier, my regret aggregated everything. Now I'm just going to care about one interval where the distribution remains stationary. Okay? So suppose now that Qx is that distribution over an interval IQ. I'm just going to look at the expected difference in mean rewards over that time, over that interval. Okay? And then the main question is, how is this affected by the previous distributions up till that interval? I hope that's clear. One quick thing is that no change point detection is needed here. There is never a need to restart. And in fact, the best rate you can get aggregate past distributions. I hope that's, that intuition is clear. And intuitive in some ways, because the mean rewards are not changing. Okay? And so since the mean rewards are not changing, we should keep learning somehow. And now the question is, how much do we keep learning? It will depend on how far the past distributions are from the current distribution. It turns out, however, that the usual stationary strategies do not work to optimally aggregate the information from the past distribution, from the past distributions. And the key point here is I have to first explain to you what the usual strategies are, and then explain to you how we are going to try and measure the information from the past distributions. I hope that's clear. All right. So here the usual assumption is that of Lipschitzness. So essentially that, so we have context over context space. The context space might be all of RD, okay? And the means are Lipschitz over this context space, or at the very least smooth in some sense, similar rewards for similar context. So since this is the case that nearby contexts have similar rewards, we can partition up the space. So that's the usual strategy. We partition up the space. We observe a context XT, maybe a patient profile. We observe the context XT, and then we're just going to try to look at the nearby context. And then you play a bandit in amongst those nearby contexts. So here you pick R. R being the size of the neighborhood that you're going to use. Okay? You pick this R, and the main problem is the choice of this R. Which R should you pick? Which neighborhood should you pick? So that's the main problem, the choice of this R. You pick a neighborhood size R, you discretize your entire space into neighborhood of small, into balls essentially of size R, of radius R. And then which R should you pick? And it will turn out that the best arm to pick depends really on that marginal distribution. Why? It should be clear here. If I pick this small one, then my regression is good. The bias of my regression is good, right? The bias of my regression is good. Nearby contexts have nearby rewards, nearby mean rewards. However, I don't have enough data points in here. So I may have to pick a bigger one and do a trade-off between variance and bias. I have a lot more data points here, so my variance goes down. So there is that trade-off, and that trade-off is controlled by the marginal distribution. So the R, the key thing to keep in mind is that the choice of R is controlled by the marginal distribution. And now we're saying that the marginal distribution is changing. So the key problem now is that choice of R. If the marginal distribution wasn't changing, then you could just pick a fixed R, which is fixed for the entire space. I hope that's clear. I'm not giving you the form of the optimal arm, but just that simple fact that you can pick a fixed R. Now, the distribution is changing over time. And in fact, in a lot of the previous works, the assumption here was that the marginal not only is not changing, it's uniform, or it's nearly uniform. Now we have to get away from all those assumptions and look at very generic marginals. It actually changes the choice of optimal R. Quite dramatically, okay? Even if it's stationary and P is just not uniform. It changes the choice of optimal R dramatically, so we had to resolve that first, understanding what the choice of optimal R is if P is not uniform. Then the key thing, the key algorithmic thing we do here is that we now choose R locally. Rather than choosing a global R, we choose R locally.
I was wondering computationally would things...
That's what I'm getting into the next one, yeah. I hope it will answer. If it doesn't, please, yeah. So we're going to choose R locally. Why? Because we are only going to care about local changes as the distribution is changing. For every context XT that we observe, we're only caring about how is it changing in that region of XT, okay? So, to make it computationally feasible, we are going to consider hierarchical partition of the space. Okay, so we consider a hierarchical partition of the space. Whenever we observe XT, so at the top of the hierarchy is the entire space. So here we made the assumption that all the observations are bounded. Okay, so the entire space is the root. And then the partition, the first level partition is this one, okay? And that's this level here. And then you refine further and further and further. All right. So when you observe xt, you just observe a path through this tree. Now the choice is really just which level in this tree should we pick. The choice of R just becomes which level in this tree should we pick. And at time t, there is really only log t levels you need to consider. And that's why you can do it efficiently. Okay. All right. And then now at every level, we play Bandit in every cell of every level. And then we just pick the right R. The choice of R happens to be roughly this choice. We pick R to be roughly 1 over square root of the number of points that fall in the cell at that level. Okay, so this NR of xt at level R, R now defines the level. At level R, we look at the number of data points in that level and then see, and this is just a bias variance trade-off, and see whether it corresponds approximately to the bias. Okay, and so that's the choice. The key point here is that this choice, that's an intuitive thing, is that NR of xt immediately automatically encodes all past distributions. It's the number of points that are in that cell at time t. It encodes all past distributions, and hence we don't have to actually do a change point detection. And all the information we want is there. I hope that's clear. Furthermore, notice this. The larger NR of xt, the smaller R, right? So we are picking a more refined area, the larger NR, and the larger NR means also that the past distributions have contributed a lot of points locally at X. So the past distributions have a lot of information at X. This is leading into how are we going to quantify the information from the past distributions. Okay? All right. So how informative is a past distribution Px to Qx? I'll just use a quick some quick pictures. So here, suppose that the support of the current distribution Qx is this, and the support of the past is this. We can tell that this is not very informative. Why? Because as we play in the past, we only observe context in here. We don't observe context here. And so once we start playing this distribution, we would not have had any information in this whole region. So this is a case where the past is not that informative. Here is a case where the past is a bit more informative. And then, intuitively, here is a case where the past is quite informative. As we play the past distribution Px, we've observed a lot of data in the regions that we care about under Qx. And so that's the key point. How much data have we observed in regions we care about under the current distribution? So this leads to this notion, which I'm going to call the transfer exponent. It's a notion that came from past work on domain adaptation. And the notion just says the following. It says that consider any radius r, and consider any ball of radius r, and let's just look at how much mass p assigns to that ball versus how much mass q assigns to that ball. And in particular, we're just caring about regions of large q mass. If a region has large q mass, does it have large p mass? That's really what this thing is saying. Okay, so I hope that's clear. And so it's a simple way to capture this notion. It's asymmetric. That's one key point I wanted to make here, is that it's asymmetric. Unlike metrics such as total variation and such, we might feel like using simple existing metrics to measure the distance between past and present. But in the examples I gave before, even in this example here, you can tell that total variation, for instance, may still be large, right? Okay, and in fact, this problem is asymmetric. You can see it here immediately that the problem is asymmetric in the sense that while P has information on Q, Q doesn't have that much information on P. There is this whole region that Q doesn't cover. Okay, so you need a notion that is asymmetric to capture this. All right. So this just leads to, I'll just give you quickly what the guarantee is that we get. So we get a guarantee of this form. on the risk on the queue, this interval regret. And the interval regret, the key point is that let NP be all the rounds that were played before we start with the new distribution queue. The regret includes that NP. I hope that distinction is clear, I hope. NQ here is just the length of that stationary phase on the queue that we are caring about. And if we hadn't incorporated the path distribution, then we'll only have a rate in terms of NQ. But here we are incorporating a rate in terms of NP. And there is a function rho here, which I don't write down, but this function rho is a function of this transfer exponent gamma that I just defined a second ago. And as gamma goes to infinity, rho goes down. Here, let me go back. Gamma goes to infinity is exactly the case where there is no information. Gamma equal to 0 is when there is information. Small gamma is a lot of information. Large gamma is no information. It's more of a distance. I hope that's clear. All right. So this is the form of the rate. And the key thing, again, is that the rate integrates the path information. These quantities, alphas here, I'll just say quickly what it is. It's a margin between arms. It captures it. For those who are familiar with Tibakov's margin condition, it just looks at the margin between arms and the distribution of the margin between arms, right? And you can imagine that the larger alpha, the easier the problem, the more margin there is between arms. And you can imagine that the problem itself gets easier the more margin we have between arms. That's a lot of signal between the arms, okay? All right, I'll get back to the margin thing in a second, all right. So here, any question here? So here, to reiterate, the main message is that we can define a notion of severity of changes and then incorporate that severity of changes. And we don't need, if we use a local method, we do not need to do any change point detection. We can keep learning in this particular case. All right, so then bringing it all together, I realized I wasn't going to have time. So I had just a sentence that it's a difficult problem to try and bring all this together, but I'll be happy to talk about it. We're still trying to define a clean measure of joint severity in changes in X and changes in YT. Okay. We have some preliminary results, though. In summary, let me say something quickly that I left out earlier. This is one of the things that's interesting. So if we're looking just at changes in XT, but not in YT, it turns out that we can get this notion of interval regret, right? We can say, I pick an interval where the distribution is stationary and say, I'm going to try to do as well as possible just in that interval. In the case where the YTs was changing, we only looked at this aggregate regret. It turns out that in terms of adaptivity, that's the only thing we can do. We haven't published that, but that's the only thing we can do. Interval regret is not possible adaptively. And so that's bringing these two ideas together somewhat tougher. We're realizing that there are certain things that we were able to do in the case of context that we cannot do in this case. And what is it that we can do in both cases together? I talked about margin a second ago. It turns out that even a notion in terms of margin, in terms of the hardness of the problem, in terms of margin in arms, is not possible if the rewards are changing, if I'm trying to adapt. That adapting to a notion of margin is not possible, which was also a bit strange. In this case here, adapting to a notion of margin was possible. Okay. And so the problem gets a lot more complicated. All right. So summary, main design element. One of the things I wanted to push here is that it's important to get a sense of the severity of changes so that we can design procedures that track only the most severe changes and stop and restart only at the most severe changes and keep learning. And in that sense, we may be able to adapt and get much better regret. And I hope this type of idea, we can push it eventually beyond contextual bandits. So that's our hope. All right, thank you.
Thanks for the interesting talk. I had a couple of questions relating to incorporating problem structure. So I often find that these agnostic approaches to adapting to distribution shift can be somewhat conservative.
I cannot fully hear you.
Okay. So questions relating to the problem structure. So for example, if you have A given x's that are quite extrapolatable, do you have a sense of how these
are quite what?
Extrapolatable across different x's? I believe you assume Lipschitzness as of now, right? I guess the most obvious extensions are to non-parametric classes, but I guess more realistically, you often have offline data where you predict, say, the gaps per x's. Do you have a sense of how your procedure can adapt to these types of structures?
So here, structures meaning maybe other notions of smoothness or some other
sure, or
information
specific prediction models.
I mean, for other notions of smoothness, that's immediate in some sense, right? That's immediate because to go from Lipschitzness to higher order smoothness, you just need to do better regression, right? However, here is an issue that we have immediately with smoothness, with any notion of smoothness in Bandit. It turns out that at the heart of Bandit, there is a hypothesis test, right? And we cannot adapt to notions of smoothness in hypothesis testing. And so it's, seemingly we cannot adapt in Bandit to the notion of smoothness. So what's sort of is not so nice in this non-parametric contextual Bandit type things is that you need to know the smoothness level a priori. And now, what else can you adapt to? It's unclear. So even that we're trying to see, okay, is there some relaxed notion of smoothness that can be adapted to? We don't know. Yeah.
I see. Thanks. My second question is, you often have cyclical shifts, or you essentially know a lot about
some structure
how the
between
shifts
the shift themselves.
Exactly.
Yeah, yeah. So we haven't thought about that.
Okay.
But those are good points. Is that some structure between the shift themselves can make things even easier. Yeah.
Thanks.
So algorithmically, like, what's the computational complexity to adapt to this R?
Oh, the gamma.
Gamma, or, yeah.
Oh,
sorry.
here
Yes.
it's immediate. The adaptation was immediate.
Right.
Right.
Yeah, gamma, yeah.
Yeah. The rate is adaptive to gamma.
Okay.
We don't
it's
know gamma
automatically
theory.
adaptive.
It's automatically adaptive to gamma.
I see.
And it's actually minimax tight.
Okay, I
Yeah.
see.
It's minimax tight by just appealing to reduction to classification, where we can show that it's tight.
Oh, I see.
Yeah.
Okay.
And yeah, and the whole point of the transfer exponent back then, actually, when we came up with it, was that there was this question in domain adaptation where people are always trying to learn the distance between distributions. And anyone who's worked on metrics or estimating distances between distributions knows that this is a very hard problem, right? And so do we need to solve that hard problem in order to solve domain adaptation in classification? And so hence, we started looking at what can we adapt to, in a sense, rather than having to estimate the distance first and then do something with it.
Right. All right. Let's thank the speaker again.